students start by reading this paragraph, or at least I had one student read the paragraph. Um, as he read the paragraph, he found that the most difficult part of reading the paragraph was the numbers, either being very, very big numbers in the billions or trillions, or being exceptionally small numbers. Um, so we looked at in science, especially when we deal with numbers that may be very, very large, very, very small, that there is a better way or a different way that you can write a number that makes it easier to read and to shorten up the length. Okay. To kind of give you that, we're going to use multiplying by a power of 10, 10 or 100, 1,000 to make it a little easier. So first of all, let's just look at what happens when we multiply by a number by power of 10. When we take a whole number, most students, pretty easy, well, they just add zeros on it. If it was 95 times 10, they add a 0. Times 100, they add 2 zeros, etc. So 95 times 1,000, we just add on 3 zeros, or 95,000. But that's not the true same when we multiply 4.55. We just don't add on 3 zeros. That really would be the exact same number. So that's not what happens. So we looked at, well, what does happen? And one of the students says, well, really is what happens is you're moving that decimal over one place for every power of 10. So times 1,000, we actually moved it over 3 places and becomes 4,500. Okay. So if we had a very long number like 730 billion, we could write that as 7.3 times 10 billion. Well, good. Does that really shorten up the number? No, not really. Does it make it easy to read? No, not really. But if we can express this as 10 to a power, well, then we can shorten it up a lot. So let's take a look at our 10 to the powers. 10 to the first power is just 10. 10 to the second power, 10 times 10 is 100. 10 to the third is 1,000, etc. So basically, whenever we have, the power, it really kind of shows us how many zeros we have in our power of 10. So if I look at this big number that I have here, which is 100 billion, really is nothing more than 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11th power. So I could say that this very large number here is really the same as 7.3 times 10 to the 11th power. As we go through the notes of this, again, you may pause the video at any time to kind of take the time to write down the notes, and then we'll look at some examples also. So scientific notation is really just a short way to write very large numbers or very small numbers using this multiplication method by a power of 10. Okay. Well, to write it in scientific notation, we simply want to put a number or decimal after the first digit that's not a 0. And I mean the first digit as I read that number from left to right. So for example, if I had a number like 4,500,000, I really wish I could take it and put a decimal right after that first decimal. And then I'd have 4.5, like that. But when you look at a number like 4.5 with all those zeros, we really don't need all those zeros because they're after a decimal. We can actually eliminate it. So we have shortened that number up from 4,500,000 to 4.5. Well, we can't just do that. Those things aren't obviously the same. So the next thing we have to do is to show the person who's looking at this number is how far we move that decimal. And we do that by multiplying by 10 to a power. Now the only thing is I got to figure out what that power is. What did I multiply by? 10, 100, 1,000, 10,000, 5? How many thousands did we multiply by? And again, we can just count our power of 10. 1, 2, 3, 4, 5, 6 places that I moved it. That would be 10 to the 6th power. So we look at our power of 10 based on how far we move that decimal. Now, we do have to be careful because if I had this problem right here as opposed to 0.0000045, this is a very small number. Now putting this in scientific notation, we still kind of go through that same process. I wish the decimal was really after this first number that's not a 0. So I wish it was just 4.5. And again, we have to show the reader how far we moved it by multiplying it by 10 to a power. And we simply count those decimal places to determine how far the power was. So if I look here, I moved it 1 place, 2 place, 3 place, 4 place, 5 place, 6 places. So in this example, I moved it 6 places. The only problem is, as you look at that, how can both of those numbers, 4,500,000 and 0.000045, be expressed the exact same way? And they can't. Well, the difference is in this first one, we actually multiplied by a power of 10. This one, the second one, we actually divided by a power of 10. Remember, when we have a negative exponent, that's like dividing. So we use, on our power of 10, we use the positive exponent for our larger numbers, and we use negative exponents for our smaller numbers because we're actually dividing by powers of 10 as opposed to multiplying. Okay. Let's go through a couple quick examples. You just kind of watch. Hopefully, again, this is fairly simple. If I look at my first example here, I like my decimal to be right there. So I actually write that 3.45, and now I can erase or eliminate all these zeros. But in order to do that, I need to multiply by a power of 10, and I simply count how far I move that decimal in order to get it there. So 3, 6, 9, 12, and then one more would be 13 places. And the second problem, I'd like to move it from here all the way till after the first place. So I'd like it to be 4.5, and then I moved it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 places. So times 10 to the negative 11th because it was being divided by that power of 10, or it was a very small number. Okay. So what I'd like you to do is to try these three examples right here. Okay. You can pause the video and then come back and watch the solution. Okay, and actually you can just try the first two problems. Okay, so problem 1, I wish this was 6.5 times 10 to the first, second, third, fourth, fifth, sixth, seventh power. And here I wish this was 5.61 to the first, second, third, fourth power times 10 to the fourth, and it was a small number, so we want to use that as negative fourth. Our assignment.
These assignments on page 217, numbers 9 through 30.